In the previous video, we introduced the state space representation for a continuous time system, which was these matrix equations down here, at least for our purposes. You might see it somewhere else in slightly different format, but the continuous time state space representation right here. And from there, we went through kind of how to solve such a thing, and I'm not going to go through that again. We had a way, at least for that state equation, how to solve it. Here was the solution. It looks a little ugly, but bear with us. There's also a discrete time or discrete version of state space representation. Some systems are naturally discrete. I don't want to get into them. Why we really care about it is we're ultimately going towards the Kalman filter. We're going to be doing things using digital computers. So we have to do things in little discrete chunks of time. So even if our system is continuous, we've got to deal with it in a digital discrete time way. Well, you have so your state vector x, I'm going to think of k's as time. Mathematically, they don't have to be time, but I think of this time k, there's a way to get to what is it at a later time, k plus 1. And generally, we're going to say those time steps are uniform, meaning they're always the same. If you do it every 1 second, or actually every 1/20th of a second, or whatever your time step is for your system, we're going to assume it's uniform for now. So that actually this z is the z at a certain time t sub k. So we measure things, we sample. It might be a continuous signal, but we're only going to measure it every so often. But notation-wise, we're just going to call it z sub k, but it will really mean the measurement at time t sub k. Anyway, here is our discrete state space representation for now. We're going to deal with this guy a little bit later. How do we want to do what's called discretization, which means we want to approximate a continuous time system with a discrete time model. What we're going to do is we're going to take time steps that are hopefully small enough that we can treat this f, even though it in general is a function of time, that we can treat it as a constant if we take a small enough time step. Then we could use the solution we had for f being constant. Here's the way to get from a time t sub k to a time t sub k plus 1 in continuous time, if f is constant. And we had a way to get this phi using the Laplace transform, where this f now is whatever f was at time t sub k. Compare that to our discrete state space model. Here was the continuous time stuff. Here was the discrete state space model. Well, the a sub k will be this state transition matrix. It was this inverse Laplace transform. And the wk, that's this part of the discrete module, is this kind of mess over here in the continuous case. So we have ways to translate it. We now know what AK is. We now know what W sub K is. So we have a discretized model. And we're going to start putting in phi here all the time. So here is the discrete time state space model. we're going to start talking about the U and V in the continuous time model as being random processes. So what are the W and V in the discrete time case? Well, we can only deal with, since they're random processes, we're going to want to find things like the mean and the variance or covariance, since everything's vectors now, or could be. So especially, what is the mean? What is this sort of variance or covariance? We're also interested in this guy. So let's go through some pain here. Here's what that W sub k was, right? What's its expectation? Mean. Well, it's the expectation of this whole mess. We can bring the expectation operator inside the integral, and the only thing that's random is the input U, not the G, not the matrix G or the transition matrix. Those are constants of your state space model. They're not random. Input is random. So that you end up with this result, but look, if the input mean is 0, the output mean is 0. That's good. And what is this guy? This covariance matrix? It means this, but I know what W sub k is. So I can find this expectation. These guys become, this product of integrals becomes a double integral. We can bring the expectation inside the integral again. The only things random are this U at 2 different times. But if this U is unity white noise, the inner integral goes away and we're left with this as our Q, as our covariance matrix of this W random process. So we're going to assume, well, if the input, if the continuous time input is 0 mean, so is this W, which is the input in discrete time. And if U is white noise, the W is also white, meaning when it's discrete, it means independent sample to sample. So that, take my word for it, this guy here is 0 if J is not equal to K. So our mean is going to be 0, this guy's going to be 0, and we have a formula for this guy. If we assume the U in the continuous time model, which is the input, is unity white noise. And we are going to assume. And there's a simplification for all that when the F and G are constant. This was that general formula. F and G are constant. It simplifies to this. And this is something students could deal with. And this is all I had my students deal with. I didn't have my students have to deal with this one so much. So they could, when making calculations, they could always assume, or the F and G were constant in the problems they were given. So this is something you could solve. Sorry for these T's having 2 different meanings. This upper limit on the integral is the time step, which is just the time difference between T sub k and T sub k plus 1. These superscript T's here mean transpose. And by the way, the easy way to do this inner guy is this way. Figure out what phi times G is, and then do this operation. So when you put all that together, we had a continuous time model, which was this, where the input mean is 0, and we assume it is unity white noise. We assume the input U here is unity white noise, zero mean unity white noise. The discrete model is this here, where phi, we have a way to compute that now using the inverse Laplace transform. The mean of that W is zero. This covariance matrix is zero if J is not equal to K. We call this covariance matrix Q sub K, and we had a way to compute that. And my students only had to worry about this guy, not this guy, which is a little bit more tedious usually to work. This guy works, and the F and G are constant. So I kind of went through all that quickly. That's an outline of modules and the calculations involved. I'll do an example in the next video. Example of discretization.